Okay, let us continue with our next example on finding the distance. And this time we're going to find the distance from a point to a plane. Okay, so a way that we can think about finding the distance from a point to a plane is to recognize that that shortest distance is going to be along the normal vector, right? That along the normal vector to the plane, I'm going to be perpendicular, and then I can just figure out the point to the plane. I can do this using projections by considering that if I have point 1, right, x1, y1, z1, whoops, let's scroll down, right, x1, y1, z1, gotta move over a bit, sorry, that if I've got that point in the plane and I've got some P naught somewhere in the plane that we'll just say is x naught, y naught, z naught, then I can think about the vector going from P naught to P1 and consider the angle between the vector and say, hey, the part of P naught to P1 that's in the direction of the normal vector is going to represent the distance from the point to that plane. All right, but how can I work with that? Well, let's think of the right triangle that's represented here, right? So where here's our normal vector and the hypotenuse is P naught to P1. Well, I know that the cosine of theta is going to be the magnitude of that normal vector divided by the magnitude of that P naught to P1. Okay, but what else do I know? I know that the cosine of this angle is also related by the dot product, and that's why we discuss the dot product being related to projections. And that is going to be that it's going to be that normal vector dotted with the P naught to P1 all over the magnitude of the normal vector, the magnitude of P naught to P1. All right. Well, what does that imply? Well, that implies that the magnitude of the normal vector, which is the distance between the point and the plane, is going to be given by the normal vector dotted with P naught to P1 all over the magnitude of the normal vector, right? Because if we have fractions that have a common denominator, right, that we can solve algebraically. Now, we end up putting absolute values around that dot product because even though the dot product is a scalar, it could output a negative value to us. And we want to talk about distance and use it as a positive value. Okay. Now, what is the directionality? What is the directionality of P naught to P1? That's nothing more than x1 minus x naught, y1 minus y naught, and z1 minus z naught, right? So that means that this normal vector dotted with p naught, p1 is going to become, and let's say that my normal vector is a, b, c, that's going to become a x1 minus x naught plus b y1 minus y naught plus z, or plus c, excuse me, z1 minus z naught. That's going to be the numerator of the magnitude of my distance, and the denominator is going to be the square root of a squared plus b squared plus c squared. All right, but what does that dot product represent? A times x1, b times y1, c times z1, and then a times x naught, b times y naught, c times z naught is a negative. Well, that really is just represented by my plane, but where the equation for my plane is in Cartesian form, but instead of equaling something, we'll set it up where it's plus d being equal to 0. So let's see how this works, okay? So I want to find the distance from this point to this plane. I first need the Cartesian equation of the plane. To find the Cartesian equation of the plane, I need my normal vector, and that normal vector is going to be the cross product of -2, 1, 3, and 1, -1, 0. I took the liberty of using my calculator to already make that computation, and I can see that that row vector is 3, 3, 1. Okay, what am I going to do with that row vector? Well, I can use that to find my distance by understanding this relationship. Right? This relationship is the relationship that we discussed up here, that distance I'm going to need to figure out the dot product between my normal vector and my directional vector. So I need the directional vector P0 to P1, and that's going to be the directional vector, right, to go from the point on my plane to the point not on my plane. So to go from 1, 0, 2 to 1, 2, 0, to go from 1 to 1, that's a change of 0. To go from 0 to 2, that's a change of 2. And to go from 2 to 0, that's a change of -2. So now I have that directional vector of P0 to P1. Okay, so what then gets represented here, right? This normal vector dotted with P0 times P1 is going to give me the following, right? That's going to give me, let's see here, P0 times the normal vector times P0 times P1 is going to be 3 times 0, right? 3 times 2, 1 times -2. And so that gives me a 1 for the numerator, right? And for the denominator, right? So once again, that was because I had 3, 3, 1 dotted with 0, 2, -2. And that's actually 6 minus 2, so that should be a 4 for the numerator. Glad we double checked. Right? And then the denominator is going to be the square root of 0 plus 4 plus 4. So that gives me 4 all over the square root of 8. And that is my distance, right? Then, what about this formula? Well, let's check out that formula. What's happening in that formula? In that formula, I have my, right, a times x1, b times y1, c times z1 plus d. Well, what's the Cartesian equation for my plane? The Cartesian equation for my plane is 3x plus 3y plus z is equal to, right, 3, 3, 1 dotted with, right, point in the plane 1, 0, 2, which happens to be, hey, equal to 5. So this formula says, hey, that distance is going to be given by, right, 3 times 0, right, oh, excuse me, 3 times 1, the point in that's not on my plane, plus 3 times 2, the point that is not on my plane, right, plus z times 0, the point that is not on my plane, and then minus 5, right, that if I took this equation here and set it equal to 0, I'd have, right, 3x, 3y, 3z, and z minus 5. So I'm going to have the magnitude of that all over the square root of 0 plus 4 plus 4. But what does this numerator give me? That gives me 3 plus 6 plus 0 minus 5, which is 4. And notice that we had that 4 in the numerator. So if we understand this relationship, I can always find the distance. But I don't have to use that relationship. I can memorize this formula. All right? So it is a useful formula, but really understand the relationships, understand where the formula got built from, and you're going to have an easier time in making the computations. There are other ways to find the distances. This is not the only way to find the distance, but it is an efficient way to find the distance using this relationship of projections. The dot product of the normal with the directional vector that you care about all over the magnitude of the normal vector that you're working with, because that normal vector will give us the perpendicular. So let's look at a couple more. To find the distance between a line and a plane that do not intersect, you just need to find the distance between a point on the line and the plane. So find the shortest distance between this line and this plane. Well, let's get our equations, right? So our line, right, is given by, let's see, 1, 2, 4 for the coordinates of the point on the line, right? My parameter t, and -2, 1, 4, the directionality of the line. And I also have, right, my plane given by 2x plus 0y plus z is equal to 1. So therefore 2x plus z minus 1 is equal to 0. And this is going to be the form of the equation that I want to use. All right. So how do I find that distance? Recognize that the formula is not part of the formula booklet. You need to understand how you could approach it without the formula, but we understand that really I care about I have a point, I have a plane, I have a normal, right? This particular point happens to be 1, 2, 4, right? And I have some general point somewhere in the plane, but I know the relationship about that point in the plane, right? And that relationship of the point in the plane, I could just figure out any point in the plane that satisfies this equation, and any point in the plane that satisfies this equation would be such as the point 0, 0, 1. Right? The point 0, 0, 1 would satisfy that point in the plane. And so I can say, hey, to go from 0 to 1, right, my P0 to P1, to go from 0 to 1 is a change of 1. To go from 0 to 2 is a change of 2. To go from 1 to 4 is a change of 3. So I need my normal vector for my plane, right? The normal vector for the plane, which is 2, 0, 1. I need to dot that with the directional vector from the plane to the point and any given point in the plane. So that's going to be 1, 2, 3. And I'm going to divide it by the square root of based on the normal vector, so the magnitude of the normal vector, which in this case would be 4 plus 1. So dot product is going to be 2 plus 0 plus 3, so that's 5 all over the square root of 5, and that is going to be my distance. All right. If I use the formula that I can memorize, but like I said, it's you don't need to. That would be saying, hey, 2 times 1, right? Because 0.1 plus 0 times 2 is 0.2 plus 1 times 4 because 0.4, then minus 1 because I need to move that 1 over to the other side. And I'm going to have all of that all over the square root of 5. All right. And look at the magnitude. So what do I have? 2 plus 4, that's 6, minus 1, that's 5. It checks out. Okay. This is the approach to use. All right, but you can certainly memorize the formula. But you need to be familiar with the approach. The approach, the relationship is what's important. So, a last one. To find the distance between two parallel planes. All right, so let's say I have one plane here and another plane there. All right, if I want the distance between those two planes, I just need to figure out the length of the normal vector between the two planes. And I can use the same approach of saying, hey, I can have a point in one plane and then some general point in the other plane. Okay, so I want the distance between these two planes. How do I know that these planes are parallel? Well, I have 2, -3, and 1. multiply by 2, multiply by 2, multiply by 2, right? But the relationship between these two is not multiply by 2. So those planes have the same normal vector, but a different position in a 3D space. So I want the distance between the planes. So I need a point on a plane, right? So I need a point on a plane. Well, let's look at this equation and let's do this by inspection and say, hey, what would be the easiest thing to solve over here? Well, the easiest thing to solve would just be to say, hey, if I had the point 0, 0, 4, that would satisfy the first equation, right? Of course, I could also do it with the point 2, 0, 0. That would satisfy the first equation, okay? Why do I want to use that first plane equation? Well, because it allows me to quickly get a value that satisfies the equation without worrying about fractions, right? I could say, hey, this is x is 7/4, y is 0, z is 0, or I could say z is negative 7/6, or y is negative 7/6, x is 0, z is 0, or I could say x is 0, y is 0, and z is 7/2 to satisfy the second equation, but why work with fractions if you don't have to? So we know a point on the plane. So there we have. So either one of those works. So I know then that that distance is going to be based on that point from the plane substituted in to the other plane. So I'm going to have 4 times 2 minus 6 times 0 plus 2 times 0. And then I'm going to say minus 7, because if I move that 7 to the other side, right, and that's going to be the magnitude of that all over the square root of, right, 16 plus 36 plus 4. So that gives me 4 times 2, that is 8, minus 7, that is 1. So that's going to give me 1 all over the square root of, let's see, 36 and 4 is 40, so all over the square root of 56. Right? If I considered the relationship approach, right, if I considered the relationship approach that this point up here happens to be 2, 0, 0, right, and the point down here, to make life simple, we said that we could use 7/4, 0, 0. Well, then my P0 to P1 distance would be to go from 7/4 to 2 is just moving by 1/4 and then 0, 0. And so I would have as well that that distance could be determined by my normal vector of my plane, which was 4, negative 6, 2, dotted with 1/4, 0, 0, which is the directionality from P0 to P1, all over the magnitude of the normal vector, which is still 16 plus 36 plus 4. And so that once again gives me 1 over the square root of 56. So different approaches. This methodology helps you understand more things. You want to memorize the formula, that's up to you. But you can also discuss it in a variety of other ways. All right. Thank you for your time. Make sure that you think about what has been discussed in these videos. Make sure that you ask questions for clarification and that you work through additional problems so that you can see the relationships that are there and then recognize that really it is the same problems over and over, just changing the numbers that go between them. But if you don't understand the relationships, it will be a lot harder to do the more difficult problems. Thank you for your time.